Okay, so let's do it.
We're live, and welcome everyone, people from the internet, for the first in-person edition of our seminar series. And now we're proud to receive Professor Daniel Rossit, and Marcus will do this introduction, and then afterwards Daniel is free to deliver his talk.
Yeah. Welcome to this talk, and thanks Anderson for managing all that stuff and for the introduction. So I'm happy that we have Professor Daniel Rossit here. He's from Argentina, from Bahia Blanca. It's in the south of Argentina. He's their staff researcher at the Mathematical Institute of Bahia Blanca, the INMAVB, and from CONICET. And he's also a teaching assistant at the engineering department of the UNS, the Universidad Nacional do Sul. And he's working in production optimization problems, something we also collaborate on, with focus on automation, Industry 4.0, and also more foundational problems like flowshop scheduling. Has very interesting papers on non-permutation flowshop scheduling, and then a lot of stuff in that. So he's really an expert in this kind of modern technologies for production optimization, and also the traditional problems and the algorithms and the complexity. And today he will talk to us about scaling problems in additive manufacturing. This is, I think, an interesting new topic also, if you think about 3D printing and stuff like that. I'm not really deep into that topic, so I'm very curious to hear what Daniel will tell us. So, Daniel, please, it's all yours.
Okay, thank you very much. Thank you also for the kind welcome and for the words. Yes, being here, I mean, very well treated by Marcus and everyone here, also invited. Well, yes, I am here in this, as Marcus said, we have the joint project of industrial red Iber, in Spanish is Red Iberoamericana Industria 4.0, in that Industria 4.0 Ibero-American network that is sponsored by CITED, and that's what this also sponsored oil is visiting. Well, this work I have been, we are working with also with a student at Bahia Blanca. It's mostly a working paper that we are doing. I will take this. And yes, the idea is to present some notions, basically, because usually when we consider additive manufacturing, we consider that that's for very special features and for prototyping. That is a kind of industrial application, but it's not for industrial production. But there are some cases where it makes sense to consider the additive manufacturing as an industrial setting or an industrial outlet for production. I mean, there is there. And so, well, the content of the presentation is rather simple. It's just we are in a case study that we are working. When it comes to production, the approach is problem because you have this problem has mainly two parts when you get to the industrial scale. That two parts are always that part, but when you get to the industrial scale problems, it makes sense to study both parts, and then you have how we approach it at both parts and the experimental some results. And the conclusions that are more of this, as I said, this working paper is just the first hints that we are getting from this paper. The really diagram of our presentation would be that additive manufacturing is kind of a single machine scheduling shop that you have only one stage of production. Usually, when you are since the production of an additive manufacturing system is very long processing times, you have several. Okay. So you have parallel machines. So this makes the problem a little harder than the single machine problem. This problem is also really hard, and then you have this part of making the things. When you are doing additive manufacturing stuff, usually the parts are they are not massive products. If you are massive product, you can compete with regular traditional production system. The idea is to have different parts, but in a huge scale, or give service to a wide audience of customers, so you have to do the problem. And then what we have is the nesting problem of putting this part into shop or into bin using the nomenclature of additive manufacturing and then the scheduling solution. Basically, what we were talking about, when you use additive manufacturing, you're trying to do special things that is hard biting them, but usual traditional mechanization operations, just for extracting material from a big larger part. So you have to do something that is very complex in geometry, and you can do it that by not by revolution or by passing the tool against the material. So you need another kind of approach. Usually, additive manufacturing allows you to do very complex systems, very complex geometry, but the big issue is that the processing is very costly, but also the material, when you are trying to do things that can resist mechanical specification, that are complex mechanical specification, and you can use it in, I mean, give service of that piece, that make all the process very costly. And this is very much, that's what is pointing in here, is much costlier than the traditional method. But the other way around is when you want to have, for traditional methods, for being competitive, you have to produce the process and the tool and the tools and the dies if you are forging and whatever. So this have very high fixed cost, I mean, the traditional method. Then this is prorated to a proportion to a large, massive loss, so that's how big. But if you are going to use a small loss or even unique loss of your product, then you are not going to produce a whole set of production and a whole environment for making just one or two pieces. I mean, that does not make sense. There, additive manufacturing became commercial and competitive, and it's there when it makes sense to consider manufacturing as an industrial scale product. Now we can say that additive manufacturing, yes, is an option for industrial production, I mean, for these special cases. Usually for aircraft system, this has been used over the last 10 years, because it's not only that it allows you to produce, for instance, this very special case of shears, but also you can, the lightweighting of that kind of pieces, because you are building the inside. So you can do that in a special feature that they use, the geometry of making this enough resistant mechanically, but you are leveling a lot of weight. The problem that we are considering here is not the traditional or the most common one, that is or at least the plastic one, that is filter efficient, that fuse the plastic filament. It's not easy for considering powder, these machines that is depicted here. This process is known as a selective melting material. That mostly what does, it has these two chambers that are symmetric by the other, they are the same chamber. And what you have inside here is the raw material is metal, but it's in powder. Like this gives you also an idea that the raw material is very expensive. But the process of this is that you have, at the very beginning, you will have this piston at the very bottom, and this one will be up high. And then you will just move this one up high a little bit, and this one a little bit behind. Just that movement is the layer that you are going to print when you action the laser scan, and you will weld the powder that is there. Why is it interesting in this case, at least for our project? Because here the process is like this, and then when this comes up, we can say that the chamber has an overflow of powder, and the roller pushes that powder into the chamber that it was moved down. So we are making these small movements continually I mean, you make the movement, the laser welds the powder, and you move again. And so the piece that you are building in this chamber is going down, and so you are constructing the building. You are getting the piece that you want in the geometry that you define by the CAD model design, and you are continually pushing the powder. The big issue here is that this chamber, probably you will produce such amount of parts that the ones that you can do in the same run. And why that? Because you can weld, the welding time that you spend for each part is fixed, and it's defined by the specification of the model, of the design, and all the specification of the product. But it's true that in the chamber you can weld this kind of inverted U part, but also you can weld here some small pieces. I mean, and if you do that, you are going to spend the time of welding that will be constant, because you are welding always the same volume, the additive of the two volumes. But this time, that is the continuous moving, slow moving of this piston and the roller, will be a proportion to 2 pieces of the only one. That's in costly is a very natural way to how this can be described as a fixed cost. And again, we are getting fixed cost that we have for making additive manufacturing, a proportion for more pieces. So you are lowering the unit cost of each piece. Going to the very beginning of the presentation, make you more competitive. We are saying that we are trying to compete with additive manufacturing to other production systems. So then, the problem that we are considering all this differentiate because what we have is we have a serial or a list of orders provided by the client, by the customer, that they define what kind of piece that they have, the geometry, specification, the geometry and materials and whatever, and the strengths, and then what you have to do the engineer and something to define. But after that, you can, if they accomplish the same, they are using, for example, the same raw material and the same welding processing, you can put them all together. If you do this in a smart way, you are going to a proportion, the fixed cost in the most large part of the amount of parts, so you are getting more efficient. If you are doing only one run for each part, you are getting very efficient. So you are going to have the welding cost and also the fixed cost for every part. And then the idea of the project is to have these two parts: the nesting, that is, make the parts group into shops or into builds, that's using manufacturing, and then to have this for shop efficiently. I mean, then once we have all the shops, scheduling the parallel machines in the stage process. For the first part, we use heuristics. For the second part, we use mathematical programming because it works well for the distance that we consider. I mean, here. Well, as I explained, there are two approaches. One for the nesting, and the second one is for the scheduling, that is regular shops. Then we have already done the nesting, we have just to schedule in a parallel machine stage. The problem that we are approaching is considering what is the point? Where is the makespan? The makespan is the object function. We are considering 3D printer that can produce more than one piece. Makes sense for the problem that we are considering. This not to consider only one. There are parallel identical machines. The machines are all the same. We have the same capacity, the same velocity, and the same production rate. And then, well, again, we are producing a production. So basically, we have considered these 4 heuristics. Basically, we consider 3. The last one is just for making the baseline for comparison. The idea here is to again to consider how to group this part into and making the jobs that accomplish with the chambers condition that we need in our machine. The 3 ideas has then in the mathematical model, I will give also a different insight of why we consider these 2 parameters. Basically, we consider volume and height as a parameter for considering the grouping. First of all, we consider a decreasing volume. Let's say you have a list of 100, 1,000 parts. You just order them from the largest volume to the top, that is the lowest volume, and you start picking up from the very beginning the ones that you can make in the grouping in shops. You will keep the first one that is allowed by the area that you have, the remaining area that you have in the chamber. I mean, once you pick the first one, yes, you know that every part is possible, it's a feasible production of your system, so you can pick the first one. But the second, you have to consider that you have already picked one and have some part of the chamber is already filled. You have to consider the remaining area. This heuristic basically what tries to give us the idea here was to test that at the very first we are considering shops, getting shops that are going to have a huge volume parts. I mean, the largest volume will be at the very beginning. So the first shops that are getting by this heuristic, they will give shops that are, you can say, dense in volume. We are going to have very sick process. And then we are moving forward in the list, and we are getting to the lower part and lowest volume. We are getting the low density. I mean, we are only getting small pieces, and so this should be the difference. I mean, we are by not in a statistical manner, just in a dispatching rule manner. We consider to separate the type of parts. The second one is the other way around. The idea is to consider more balanced shops and see what happens. The idea is just for experience, experiential work. Well, I'm forgetting this. What do we do? Again, we order all the parts from the very largest volume to the lowest volume, and we take firstly the largest volume, and then we start taking from the bottom up high. So we take the lowest volume, again, that can get inside the remaining area that is left in the chamber, and you get like this. When you are doing this, you are mixing in the same shop large volume with the small volume, and in an ideal manner, because it's not like this, but because it's all like discrete things, it's not continuous, but you are getting the pieces. You can say that parts are the first, you are going to have large parts inside, but with the small ones, and then you are getting to the middle that it will be more balanced in volume within all the shops that you are producing. What's the main idea? To test the scheduling. It's better to have different kind of shops or the most regular one, because the volume impacts directly in the shop processing time that you have in the processing. And the last one is similar to the first one, with considering the heights. Here it doesn't make sense to do something similar because the volume, yes, because it's proportional to the height is proportional to the processing time, but we just only run this one. It's similar to the first one, considering the height. And the last one is just group it randomly, making sure that you can process it. I mean, that you don't have more pieces than the one that can settle inside the chamber. Well, the mathematical model, well, this is the notation, just the AJ is the area that the shop shape will have all the parts that composite. A consideration how we consider the area is just to consider the area that is projected into the flat area of the chamber in the widest, you can say the widest part of the part. I mean, we take the widest part and project it to the very bottom, and this will be kind of a prisma for following the geometry. It's not necessarily a prisma, but you are getting that area over. You can say that it's already over that area. The volume is the volume strictly of the pieces, and then well, that's all the parameters. There is a setup time for the machine and the maximum height and whatever. The instances that we took, they are from the literature. It was basically what the model is for optimizing the makespan, as was already said. Basically, what the model does is to assign the different shops to the different parallel machine, ensuring feasibility. And basically, what I would like to show you is that the GPT that remains the processing time of shop P and machine M, and this is proportional, as I said, of the volume of the shop. That the volume of the shop is built by the heuristic, considering the parts that you group inside, and also proportional to the height of that part. Considering these two fixed parameters, the little one is proportional to the shop, and the first one is proportional to the machine. Volume was more important than HT in time, so that's why we want to say two bases in volume and volume. And then anyway, this what I lost.
See if the cursor has
Right.
Okay.
And that's okay.
Yeah, I have to position right in the
It doesn't work. Okay. Here, as I said, this experiment are using this data that is from this paper, but this paper is based on a case study done in UK. The author they are from Exeter University. Well, the middle one now is not anymore there, but he's still collaborating with people from there. And the case is from aircraft, something like that from UK. Well, there is the paper, you can get the information. The instances were get almost up to 1,000 parts, and the machines you get only after 50 machines. They also consider different cases that where the machines are not the same, we just consider here all the same machine because the idea, as I said, the beginning of the project was to consider which is the more important part in the I mean, we are industrial engineers, so we're trying to understand which part is most costly than the other. So the idea was to say what happened more if the volume of the height and all. And here are the results. All the results have been done considering already the output of the heuristic, so they are solved optimally by the assigning model that was presented behind. And as we can see here, basically the one that, well, these are the instances that we tested. We didn't, sorry, one part say that something that I didn't say in the first slide was that we didn't test every part with every kind of machine. Just we consider small problems that also is natural for industrial settings. I mean, you are considering you have not too much treating machines in parallel. You are considering you have some demand. If you have large demand, you will have larger facilities. That's a natural thing because also it doesn't make sense to consider 50 machines to build only 100 parts. We just assign directly. We already will have hidden machines. That doesn't make sense. And that's the result considering the different partition building with the heuristics. The first one is a random, that is just grouping them accomplishing capacity, decreasing volume, the distribute volume, that is the balanced one, and the last one was the decreasing height. The one that is bold and underlined is the one that is the best in every line. As we see, we missed, I don't know why, this value. Was talking with Chanel, and we don't know where it was lost in the cloud. Because it's not the well, and here also the one that is the best is the decreasing volume, but usually the decreasing height is the best one. We have this one. This is, you can say, strange case that is where random get wins and get wins by far. Now we have a more insightful table because this item. Here it's 0 if it's the best. I mean, this is a comparison of the percentage deviation from the best result. If 0, you are in the best result, then you are percentage deviation to that. So we see here that the most 0 ones are set in the decreasing height, and usually that they have you can to compare the decreasing volume is best than the distributed volume. And usually it gets also the decreasing volume gets better than the random one. This piece of experiment, it was like that. We think that something like it has some yet for every when you get the square problem, usually it can be a kind of hard, but that's just a very, very hypothetical thing. I think we are aware that this result strange because also it's not that only the random ones, it's not only the largest difference between the other. So there is something different. For the other cases that they are more stable, the situation we can say that decreasing height is the best, following by the decreasing volume, and then the distributed volume is worse or at least similar to the random one. And this also is this perhaps it helps us more for the following future line, you can say, because this means that having all the shocks that are, we can say that have the same processing time, that is assigning process, having very uniform build, doesn't make efficiency. It's better to have that one, and you can put in the pieces of the, you can say, we are making a production set, we can consider so a Gantt chart. So having large one and small ones allows you to have a better combination. It's not a very large difference, you are around 1% or 2% or lower, but it makes sense to have the largest one and the smallest one pieces and not have all the same pieces. At least from this very presentation. So the conclusion that we arrive at the future line is here. Thank you. Questions. The idea is, well, the approach, it was already implementing some ideas similar was done in the literature. They approach the generating problem by an heuristic, by a some kind of sorting. So we provide some new, but if we can say that it's calculable that we get enough good solution, we can say, because the makespan and the solution was kind of very compact. I mean, probably you can do a bit better if we continue improving the heuristic, but it doesn't seem that it remains a lot of time, because when when you consider how the compensation of the larger and smallest one, you say, oh, perhaps you can get something interesting, but you don't know. But it's scalable. I mean, you get good solution. The geometry of the part naturally is a good line for considering the netting. I mean, when you are going to group the parts, it's interesting to consider the geometry. Another thing, and also going a bit more in deep, the vocation show doesn't seem to be very fruitful, because as I said, it was the worst, or nearly the worst. So the idea of the geometry is getting good, but also then, since this is for printed material, I mean, the additive manufacturing production environment, usually, yes, the ones that make for instance, the large production is made for themselves, but it's common that you outsource this kind of production, this system. I mean, the business environment is not that the one that have all the machine, the printing machine, is the one that needs the production system. Usually, there are people that do this kind of thing because, return to the beginning, I mean, you don't use this technology for every part that you need. So the demand of this kind of thing is kind of, you really need to have a good need, I mean, a good demand of that. So mostly what is that happening is that an industry that dedicate to provide services of additive manufacturing to other industries. That means that you are getting naturally the customer client, the orders that you receive are from outside, not from you, and so you are not managing that demand. And also that's why all this explanation, because it's good to optimize the geometry of the nesting, but also that is not considered here. Another step, and this is something of the implementation, is that usually this part comes from different clients, and you will have at least different due dates, at least. Then you will have also different kind of restriction that you have to provide. For instance, they would like to have all the pieces in the same bill, and special services that you can provide to your client. So it's also that the geometry, I mean, the nesting can be improved in that part, but also we are aware that we need to improve this also another feature of the system, because the business is like that. I mean, it's not that you are processing for yourself. You need to do your work, so the due dates are a must, or it should be a must in the chair. And also for extended experimentation, the ones that we are considering will happen if the quality of the printing, because here we consider homogeneous processing time. That's not a variable process. If you are considering when you're, when you print the surface of the printed part, is usually, if you do it in a fast manner, you get a very worse part. But usually when you are doing it with metal, I mean, this is more material science, the crystallography of these parts is getting very porous. You get the small bubbles is compared inside. And if you do it in a fast manner, so that's also not challenging the quality of the surface, but also the mechanical properties of the piece. So you must, the quality is a very interesting topic to play, because you can do it in a very slow manner, but then you can, because this kind of, usually this kind, some of these machines, in your laser you can print thicker layers, but you can do that also in the same run, in the same powder. I mean, you can push one powder and print, but if you want another part here that doesn't have so much quality, you can put two powder layer and print it only one. Print the two layers together. That will be a lower quality but cheaper manner, and if for the client it's okay, for the specification is private, you can do that. So this kind of issues make the problem. I mean, this, as I said, is future lines. This is a working paper. So if anyone would like to know more or to do something with that, feel free to contact me, or just I can give you material for yourself as well. Thank you very much. If there is any question.
Thank you. Thank you, Professor. Questions?
I have a couple of questions.
I have one question.
Yeah.
With respect to the nesting problem, do we really have a description of the nesting problem as an optimization problem? Do we have an objective function, for example? What do we want out of the solution of the nesting problem?
Yeah, we have something that we have. Because nesting problem is kind of a pin packing problem. You can consider that. That's the main family of that kind of problem when you put inside here. The approach that we do, what we did here, is just a straightforward approach. And we say, well, we are making this heuristic, this, you can say, good idea or reasonable ideas for grouping the path. But we don't have a special, I mean, we can compare the outputs of this heuristic because it's kind of, you don't have many. The idea, that's why we come to schedule and say, well, this is the one that is getting better result. It's a very straightforward approach. The problem is when you get all the problems together, I mean the nesting and scheduling problems, they are both ethical problems. So getting two problems ethical in the same run, I mean, at least for, as I said at the beginning, was just we are working in the project. The first step is, well, we are not kind of like the Everest in the first mountain that I want to climb. Just go to some stairs and look upside, oh, okay, I'm here, we can move. Yeah.
Maybe connecting to that, I have a couple of questions. First, with respect to the model, I don't know if the model is completely clear, because I have this piston, right, with the volume,
Yeah.
and then you consider, I saw you consider area and volume. What is the restriction with respect to area? The projected area cannot overlap.
No, you cannot overlap.
Cannot overlap.
No, you cannot overlap.
So you can put two pieces, one
No,
above the other.
in this kind.
Projected area cannot overlap, and then obviously volumes do not overlap. That's a consequence. You don't have to do like a geometry.
No, exactly. But the area allows it, makes it. Sorry, I interrupted.
No, that's what.
Why you consider the whole thing? The question is.
No. It's just about it wasn't clear about the restriction. This kind. So your areas, projected area cannot overlap. The projected volume, the areas coming from the projected volume cannot overlap.
No, the area can overlap, and it's just a special feature that why. I mean, but usually also when you do powder setting material, you have to leave some space, some tolerance, because when you weld some part, you can, you take. You are with
volumes down.
Yeah, exactly, because you are considering very heating in a too high temperature, so you can make an irregularization to the other part. So you need some tolerance there. But the volume is because the process time is proportional to that, and the area just for making assignment of considering the capacity of the machine.
And can you rotate the pieces?
No, here not. No, that's why we are talking about
put it side by side into the one.
Exactly.
Okay.
And also no put it overlapping down.
Yeah, that makes. And other parts, is there any restriction on the parts? Are they convex, for example? Can it be concave parts? Or like everything?
Because when you guys, for instance, you have something like this, and you will, this piece, I will say from here, I will say, I will consider the largest cylinder and go upscale. Yeah. And that's the volume. No, the volume, no. The volume is provided by the.
No, you embed it into the largest cylinder.
Exactly.
So it has kind of a cylinder packing. No, if you look at it in the cylinder, you have a sphere packing into. You're packing spheres. You're packing circles into a circle.
Yeah, but no, the packing per the area is considered the square, the prismatic.
Only box?
Yes, only box. but the volume of printing is considered the real volume because you get it from the CAD file. Because the one is, I mean, when we consider, that's an approximation, but that paper, that's the same. I mean, we consider the prismatic area just for, this is the chamber, so we'll not overlap them, but the printing volume that is proportional to the running time is from the CAD file.
This from the true.
The true volume, because yeah, they get from the CAM, the computer system manufacturing, you get the volume, and they are reliable.
And I'm also interested if you look at, I mean, the instance have like 100 to 1,000 parts.
Yeah.
How many jobs get you out of them?
It was around 30.
30?
It
So
depends.
like-
I mean,
like
we consider it depends mostly in the machines because you are grouping up to the chamber allows you. It was around 20 and 30 shops for 200 shops, 200 parts.
Yeah, so like 10 parts per job, something like that.
Yes, or 3 or 4 parts. It depends if you are 150.
How does this compare to the? I mean, you have an obvious volume below bound. Take the whole volume divided by the maximum volume size, and it gives you the minimum number of jobs. How much about?
How much of that?
Is job below bound?
No, we didn't test it. For having a baseline, we use the random assignment because when I mean, the lower bound, I mean, the idea was to consider, yes, we can consider as a continuum have a lower bound. But yes, and it will be as.
This would like the sum of the volume.
And yes, and divided by the chamber.
Divided by the
And chamber, and you say, well, that's if everyone would be. Yeah, that would work, but yeah, I have, because as I said, because we didn't consider the 3D parts. So when you consider the volume and the area, the most appropriate approach would be the 3D impact in 3D. But also another issue that would be really interesting for is to group the part that have, for instance, the same due date. For instance, so you are because this kind of run can take, for instance, 2 days. So if you put something that is very in the behind, you are going to 15 days. If you make it easily, so due dates becomes also critical for at least for the instances that they are here.
Curiosity, it seems that it makes all sense when you're talking about 3D printers, but where there is this kind of research or application, how recent is this? I mean, were there earlier papers or earlier research on this?
Yes, I mean, this paper that
earlier technologies prior to 3D printers, just a curiosity.
I mean, I think that the impression that you get when you see here the academy is behind the industry, because the first paper that we consider is production planning and whatever but also I think that it not only behind, because this kind of business that is, well, I have a lot of printing machine and I offer printing services, so I can take the demands from outside. This is easy. It's not so old. But for instance, aircraft like Boeing and that kind of industries have been using this technology for the last 15 years. Exactly, but they are also very aware of that, because you are making the same pieces, weighting it a half or a quarter or even less, because you make the inside the material you make, you don't make it dense. You are only making the pan orthogonal things in octagonal things inside. So you generate the same size, the same piece. You can get it made. Usually in traditional processing, you are going to have a cylinder and you are going to put all, and now you start printing. So inside, you don't need to be solid. You can have this octagonal parts. And so that's the main thing. And this kind of stuff, this paper that is there, is one of the very, very first ones. There is a very good one that is a review, but also makes a inside the problem, and a taxonomy of the entire problem, also consider the nesting and scheduling and how the production setting is set it. That is from O and collaborators, OH, and it's 2020. That So the literature about this kind of problem is 5-6 years.
It's an emergent field.
Exactly.
Yes.
But this kind of problem, the other one, I'm not saying that additive manufacturing is how you want.
I have one more question about the scaling problem. So the
Yes.
scaling problem is like a parallel machine scaling problem with homogeneous machines,
Yeah.
and processing times are no further restrictions. It is
Yes.
It's the P bar C max.
Yes.
This is okay. So this you can solve exactly like for large instances.
Yes. That's the one we use mathematical programming. Just we don't.
Okay.
Yes, we don't care about anything because they say, well,
that doesn't make a difference.
Exactly.
Okay.
Yeah.
How much does it take?
No, for the largest one, it was just, I mean, the mid model, it take also 60 seconds, I think, and we didn't get to the 0.0 gap.
Oh.
It was just, we cut it 0.5 and say, well, that's all.
But it's fast.
Yes.
Because this could be reduced to 6 milliseconds if you want.
Well,
Yeah,
that would be also a nice part. And also another problem that is now taking advantage is because, well, you take all the parts that are already printed, you have mostly earth surface problem, so you need traditional operations just to make the turnover and whatever to pull to get the surface requirement that you need to run. So you need a post-processing time. What I mean, the post-processing is much more faster than the previous one, but the problem is when you lay out a build, you list up several parts, and probably the post-processing would demand different setup time for each, not for each, but for example, you are going to take out of a build 6 different parts. The 6 different parts, they will have 6 setups. So they are also, again, if you want to make the problem in a global manner, in an holistic manner, you may consider that, and also that is a new problem that you consider. And they also are trying to do that by robots. From Japan, they were to also that they have made some paper there and considering that with the parts, making rules for the grouping, considering the post-processing. But again, the grouping, the nesting problem, it wasn't the 3D beam packing problem. It was just something like this. Something similar, easily, that allows you to, when you get out of the machine, some more easily post-processing. Not very in-depth.
Yeah, we are approaching, I think, the time limit. I don't know. I have one final difficult question for you. What is the probability that Argentina will win against Poland?
I vamos.
Undecidable.
No, if it doesn't win, Argentina will burn out again. We are not prepared for that. No. Well, we have to be humble and accept that they defeated, but no, we are not so humble.
Thank you very much.
Nah.
Let's take a presenter again.
I'll finish the transmission here.
Thank you very much. No, thank you.
Yeah.
Thank you for coming. No problem.